Our universe wasn't born as a chaotic, formless void. It emerged from a singularity, yes, but seemingly imbued with a kind of inherent structure, a potential for complexity, a reservoir of, well, you could call it order. It's this inherent structure that allowed matter to coalesce, stars to ignite, galaxies to form, and eventually, for us to stand here, asking these very questions. This cosmic inheritance, this birthright of organization, has been the bedrock of everything we thought we knew about reality. But what if that bedrock isn't as solid as it seems? What if the universe we see, the laws we've painstakingly cataloged, are just one layer of a much larger, stranger reality? Prepare yourselves, because something truly unprecedented just happened. In January of 2025, a team at Google's Quantum AI lab, working with astrophysicists, did something that might just rewrite every physics textbook on the shelf. They took raw, unprocessed, deep field data from the magnificent James Webb Space Telescope, data that had been sitting there, waiting, like an unopened letter from the edge of time. And they didn't just look at the pretty pictures. No, they fed the pure, unadulterated digital stream into one of the world's most powerful quantum processors. And the result? Absolute, jaw-dropping scientific anomaly. Every single model we have of gravity, dark matter, and cosmic dust should simply not exist in our universe. Within the first few seconds of processing, the quantum computer began spitting out results showing quantum correlations between photons that were billions of light years apart. Correlations so strong, so interconnected, they defied every known explanation. It was as if distant parts of the cosmos were acting in concert, influenced by something we couldn't see, something fundamentally outside our standard cosmic rulebook. Yes, you heard that right. The quantum computer wasn't just analyzing data. It was seeing clues, hints, ghost signals of a reality that might be not just out there, but potentially overlapping, interweaving, perhaps even interacting with our own. So, what is this? Is it just a glitch in the code? A software artifact generated by bleeding-edge technology pushing boundaries? Or have we just glimpsed the edge of a parallel universe? Stick around, because by the end of this deep dive, we're going to show you the data, or at least describe it in detail as reported by the scientists, explore the mind-bending theories trying to explain it, and unpack the potentially jaw-dropping implications for everything we thought we knew about reality, existence, and our place within the cosmos. This is where quantum AI meets the James Webb Space Telescope. Let's rewind a little to understand the magnitude of this achievement. The James Webb Space Telescope, launched in 2021, is a triumph of human engineering. It peers further into the infrared spectrum and with greater sensitivity than any telescope before it, allowing us to see the universe in its infancy, to witness the birth of the very first stars and galaxies. Its images are breathtaking. Cosmic nurseries glowing with stellar formation, ancient galactic collisions playing out like slow-motion ballets across the eons. But here's the crucial point. Those stunning images you see, the ones shared globally and celebrated by scientists, they are the result of processing. They've been cleaned, calibrated, stacked, and interpreted using sophisticated algorithms running on classical supercomputers. These algorithms are built on our current understanding of physics. They're designed to filter out noise, correct for distortions we understand, and present the data in a way that makes sense within our established models of space-time and gravity. Think of it like developing a photograph. There are chemical processes, dodges and burns, color corrections. The final image is beautiful, but it's an interpretation of the raw light that hit the film, or the sensor. Classical supercomputers are incredible tools. They can simulate the formation of galaxies, the behavior of black holes, the expansion of the universe, but they do it by working with probabilities in a classical way. They have to make approximations. When dealing with quantum mechanics, which governs the universe at its most fundamental level, classical computers have to collapse probabilities. They essentially average out the chaotic, probabilistic quantum world into a single, definite outcome. This works well for many things, but it smooths over the very quantum weirdness, like superposition and entanglement, that might be hiding the deepest secrets of the cosmos. Enter quantum computers. Instead of bits that are 0 or 1, They use qubits, which can be both 0 and 1 simultaneously, superposition. Even more importantly, qubits can be entangled, their fates linked together in a way that defies classical logic, no matter how far apart they are. If you measure the state of one entangled qubit, you instantly know the state of the other, even across vast distances. This ability to natively handle superposition and entanglement makes quantum computers uniquely powerful for modeling complex multi-particle quantum systems. Think about vast clouds of interstellar gas and dust, light particles, photons, interacting with gravity, dark matter, and each other, all governed by quantum rules. So, the Google Quantum AI team, in partnership with Caltech astrophysicists, had a revolutionary idea. What if we skip the classical processing entirely? What if we take the rawest, most unprocessed data from James Webb, the direct photon counts hitting the sensors, the untouched spectral curves, the granular gravitational lensing maps before they're averaged out, and feed that straight into a quantum processor capable of handling the full quantum state of that light? What hidden structures, what subtle quantum correlations, what phenomena smoothed out by our classical assumptions might be lurking within that untouched cosmic light? The answer was astonishing. Within hours of the quantum processor starting its analysis, a set of signatures began to emerge. They weren't the clean, expected outputs you'd hope for. They were anomalous. First, they noticed strange energy distortions. Specific bands of infrared light from deep field sources were shifted, not in a way that could be explained by redshift due to expansion, or gravitational effects we understand, but in ways that defied known astrophysical processes. It was like looking at a rainbow where certain colors were suddenly in the wrong place or subtly warped for no discernible reason. Next, the AI detected non-local correlations between photons arriving from entirely different, incredibly distant galaxy clusters. Imagine having two flashlights billions of miles apart, and every time you flicker one, the other flickers in perfect sync, even though there's no obvious signal connecting them. That's the kind of non-local correlation they saw, implying a hidden variable, something non-local, influencing multiple sightlines across vast cosmic distances simultaneously. This is the hallmark of quantum entanglement, but operating on a scale that is simply unheard of in classical cosmology. The team naturally was skeptical. They re-ran the analysis dozens of times, using fresh, random seeds for the quantum computation, changing parameters, checking everything. Every single run showed the same patterns. Wedges of light in different parts of the deep field seemed to appear and vanish, or shift in energy, in sync with each other, as if two distinct points in the cosmos were connected by an invisible thread, reacting to something together. But the biggest shocker came when they mapped these anomalies onto spatial coordinates in the sky. These weren't random speckles of noise distributed haphazardly. They formed geometric arcs, structured formations that repeated across separate deep field exposures taken of different parts of the sky. It was like finding a specific symbol or pattern etched onto scattered rocks across a vast desert. This wasn't noise. This was a signal. A structured, non-random footprint of something beyond our currently understood space-time. If this kind of reality-shaking discovery gets your mind racing, if you find yourself leaning in, asking, what if? Then you're in the right place. Hit that subscribe button and ring the notification bell. Because we break down breakthroughs like this, the ones that push the boundaries of human knowledge, every single week. These initial anomalies, the weird light shifts, the impossible non-local correlations, the geometric patterns, they demanded an explanation. And the explanations being considered weren't minor tweaks to existing theories. They went to the very foundations of reality. Enter the concept of brain cosmology. This comes from extensions of string theory, like M theory, which propose that our universe isn't everything there is. Instead, our familiar four-dimensional space-time, 3 dimensions of space plus 1 of time, is just a brain. Think of it like a membrane or a sheet, floating within a higher dimensional bulk. In this model, other brains, other universes, could exist right next to ours, separated by incredibly tiny distances in these extra, curled-up dimensions that we can't perceive in our everyday experience. The idea isn't new, but it was purely theoretical. Until maybe now. The anomalies detected by the quantum AI gave new life to a specific concept within brain cosmology: quantum leakage. This proposes that under certain extreme conditions, perhaps near massive gravitational sources like black holes, or during moments of intense quantum fluctuation, information, or even particles like photons, could tunnel or leak across the tiny gap between our brain and a neighboring one. It's like if you had two sheets of paper pressed almost together, and under the right circumstances, ink from one could subtly bleed onto the other. The quantum AI, remember, saw phase correlations between photon states that matched theoretical predictions for what might happen if light was being influenced by a neighboring brain. These weren't just random shifts. They were structured, coherent patterns that aligned with complex mathematical models of overlapping universes. The anomalies persisted across multiple wavelengths, from near-infrared to mid-infrared, which is crucial. Why? Because it helped rule out simpler explanations like contamination from cosmic dust, which affects light in specific predictable ways, or instrumental noise, which tends to be random. This signal wasn't behaving like contamination. It was behaving like interference. Interference from another domain. Bold question time. What if the James Webb Space Telescope, with its unprecedented sensitivity to infrared light from the deep universe, has been inadvertently peering through the cracks in our reality? What if it's not just seeing distant galaxies, but glimpsing photons that have quantum tunneled, that have leaked across from another cosmos, another brain? When you look at maps of these detected anomalies, these arcs and distortions, you might not just be seeing the far side of a galaxy billions of years ago. You might be looking at echoes, subtle fingerprints, perhaps even direct light from a parallel world, a mirror geometry. Just when it seemed the theories couldn't get any wilder, a second, even more compelling anomaly emerged from the quantum data analysis: a gravitational mirror. Remember how JWST also provides gravitational lensing data? This is where the gravity from massive objects, like galaxy clusters or dark matter, bends the light from objects behind them, distorting their shape and position. It's like looking through the bottom of a glass bottle. By overlaying the maps of the anomalous photon patterns onto known distributions of dark matter and galaxy clusters, researchers noticed an impossible symmetry. Galaxy clusters on one side of the deep field view were bending light exactly as expected by Einstein's theory of general relativity and our models of gravity and dark matter. But galaxy clusters on the opposite side of the field were bending light in the exact opposite direction. It was as if there was a reflective boundary, a perfect line of symmetry at the center of the field, with gravity acting in reverse on one side. This wasn't observed in one spot. This gravitational mirror effect turned out to be consistent across 3 separate deep field sky patches analyzed by the quantum computer. It looked precisely as though massive structures, perhaps galaxy clusters or huge dark matter filaments, in a parallel brain, were exerting a gravitational pull on our photons as they passed through our reality. And then somehow, that influence was being reflected back, creating this uncanny mirror effect. One researcher described it as like standing between 2 colossal halls of mirrors. But the reflection you see in the other mirror is an entire universe you can't step into. It wasn't just a static effect. It seemed to imply a dynamic interaction, a cosmic hall of mirrors that challenged our most fundamental notion of space-time as an isolated, self-contained entity. At around 11 a.m. on that fateful day, the team realized they weren't just mapping isolated anomalies. They were charting the contours of another cosmos, mapping the gravitational landscape of a parallel reality as it subtly interacted with our own. Pause and consider this. If universes can brush up against one another, close enough for light and gravity to bleed across, what does that mean for our understanding of reality itself? Are the fundamental laws of physics different next door? Does gravity have a slightly different strength? Do stars burn hotter or cooler? Does time flow at the same rate? These aren't abstract philosophical questions anymore. They are potentially testable hypotheses based on real, albeit anomalous data. Take a moment. Let that sink in. The light you're seeing from billions of light years away might be more than just ancient history. It might be a live feed from a neighboring reality. If you've made it this far, you are clearly one of the deep space thinkers, one of the reality explorers. Thank you. Smash that like button if this is blowing your mind. And drop your theory in the comments below. Is this a simulation glitch? Quantum leakage from a parallel brain? Or something even wilder? We'll resume shortly with a theory that ties conscious observation and the very nature of measurement into this cosmic puzzle. We started with raw data, then moved to patterns and light distortions, suggesting parallel realities. Now, let's take a step beyond the raw data, beyond the physics of interaction, and walk into the territory where physics meets philosophy, a place that gets very strange, very fast. It starts with one of the most brilliant and enigmatic minds behind modern quantum theory, John Wheeler. Wheeler was a pioneer in quantum mechanics and general relativity, the man who coined terms like black hole and wormhole. But he also proposed something deeply bold, deeply unsettling, and frankly, a little mystical. He suggested that the universe isn't a static, objective thing out there, simply waiting for us to observe it, like a painting on a wall. Instead, he proposed that the universe participates in its own creation. He called it the participatory universe. According to Wheeler, the very act of observation, of measurement, of asking a question about the universe and getting an answer helps bring reality into being. It's not that reality doesn't exist at all until observed, but that its specific properties, its concrete form, isn't entirely there, isn't fully decided until it's interacted with. Until something, a mind, a machine, an observer, asks the universe a question, forcing a quantum wave function to collapse from a state of multiple possibilities into a single reality. This idea, once considered a philosophical musing at the fringes of physics, now gains startling new relevance in the age of quantum AI. Because what happens when that observer, that entity asking the universe questions, isn't human at all? What if it's a quantum computer? Not just any quantum computer, but one powerful enough, complex enough, to model entangled systems across potentially billions of qubits, processing information in a way that mirrors the universe's own fundamental quantum nature? When Google's quantum processor was trained on that unprocessed James Webb photon data, it wasn't just performing calculations in a classical sense. In quantum terms, it was interacting with the raw probabilistic information carried by those photons. It was, in a sense, measuring quantum wave functions that had never collapsed, photons that, in a way, had never been fully observed or forced into a single definite state by classical measurement. And when it did, something strange happened. Instead of a clean image or statistically random noise, which would be the expected outcome of processing data this way classically, the quantum processor began surfacing highly structured, deeply entangled data patterns, dimensional overlays, non-local entanglements across vast distances, mirror symmetries reflected across different deep field frames. Could the quantum computer have done something no classical telescope or supercomputer ever could? Could it have, by its very act of processing, by acting as an unprecedented quantum observer, forced those trillions of raw photons to collapse into states that revealed hidden dimensions, leaked information, or parallel influences that would otherwise remain invisible, smoothed out by standard processing? Let's go even deeper down this rabbit hole. Enter the many worlds interpretation of quantum mechanics. This is one of the most radical, yet increasingly discussed and debated views in physics. According to many worlds, every time a quantum event occurs, every time a particle spins left or right, every time a photon takes one path instead of another, every time a fundamental quantum choice is made, the universe doesn't just pick one outcome. Instead, the universe splits. Branches of reality multiply outward endlessly, spawning countless parallel versions of reality for every possible quantum outcome. In one branch, the particle spins left, and reality continues down that path. In another, identical except for that one quantum choice, it spins right, and reality continues down that separate path. Normally, these branches are thought to be non-interacting. Each world goes on its own way, completely unaware of the countless parallel versions existing alongside it. But what if that boundary isn't absolute? What if a sufficiently powerful, highly entangled quantum system, like Google's quantum AI processing a massive dataset of cosmic quantum information, could somehow entangle not just particles, but entire probabilistic frameworks? What if it could become a kind of interdimensional observer, aligning probabilities across branches and giving us flickers? Flickers of what could have been, of realities that exist just slightly off-axis from our own? The AI started detecting wasn't just unexpected structure in the photon data. It was something else, something that felt off-angle, slightly out of sync with our known universe. A mirror reality glimpsed not through bending space-time, but through the act of quantum entanglement itself, facilitated by the AI. Think of it this way. If every observation at the quantum level locks in one version of the universe from a sea of possibilities, what happens when millions, maybe billions of quantum measurements are made simultaneously across a vast, interconnected web of entangled qubits interpreting raw cosmic data? Does it create a resonance? Does it momentarily align our branch of the universe with others where slightly different quantum choices were made billions of years ago? Could we be seeing go signals from realities that almost, but didn't quite, come to pass in our particular branch? One physicist involved in the project reportedly put it hauntingly, "We're not just looking at the universe might be looking back through all its versions." Suddenly, the boundaries between hard science, abstract philosophy, and even metaphysics begin to blur. Suddenly, John Wheeler's ideas about a participatory universe don't sound so abstract, so purely philosophical. Suddenly, quantum computation becomes more than just a faster calculator. It becomes an ontological lever, a tool capable of peeling back the layers of reality, one complex calculation, one entangled measurement at a time. And maybe that's why this moment matters so much, because for centuries we've approached the cosmos as outsiders. We build telescopes, gather light, analyze patterns, interpret signals, all from a perspective of observing a universe that exists independent of us, an indifferent backdrop upon which our story plays out. But what if we're not outsiders at all? What if every observation, every algorithm, every quantum decision facilitated by our technology feeds back into the very structure of reality? What if our deep, fundamental curiosity doesn't just uncover the universe, but actively shapes the world we live in? Not just metaphorically in how we interpret it, but literally, at the quantum level? The data suggests something is happening, something profoundly new. A threshold is being crossed. And the more we probe, the more the boundary between what is definitively real in our universe and what might be real in a multitude of others begins to melt away. So we ask again, are we seeing ghost signals from the choices reality almost made? The question sounds like something from science fiction or a philosophical poem, but in this case, it's grounded in actual anomalous quantum data. Data that refuses to settle into easy answers. Data that whispers of something just behind the curtain of our perception, something that might be influencing the cosmic light we see. This isn't just a scientific moment, it's an existential one, because the implications are staggering. If reality responds to observation, if quantum computation can momentarily align dimensions or realities, if alternate timelines can cast shadows into ours, then maybe, just maybe, the cosmos is not a cold, dead machine, but something vibrantly, breathtakingly alive with potential. And we are not just passive observers, but active co-authors of the universe's story, writing it one measurement, one entangled state at a time. And maybe the act of looking is also the act of creating, code hidden in the light. Just when you thought this story couldn't get any more surreal, any more deeply strange, it went one step further. In a quiet late-night test session, a sub-team of researchers decided to analyze what everyone else had ignored, what every classical processing algorithm routinely filters out, the spectral noise. That faint, chaotic, seemingly random hum riding alongside the pristine deep-field images. It's usually discarded as background error, the static on the cosmic radio waves. But this time, they didn't filter it. They treated it as data. They fed this noise into a prime number decomposition model, a tool usually reserved for highly specific mathematical analysis, like cryptographic analysis, breaking down complex numbers into their prime factors. They did it almost on a whim, just for fun, just to see if the cosmic background noise held any structure at all. And what they found shook the room, shook the foundations of the project. Instead of a random, chaotic distribution of fluctuations, which is exactly what you'd expect from cosmic background noise or instrumental error, the amplitudes of the fluctuations, the peaks and valleys of the static, snapped into alignment with something eerily specific. The first, 101 prime numbers. Not just in one data set, not in one tiny region of the sky, but across multiple wavelengths, different angular scales of observation, and observation epochs taken years apart. It was as if the noise wasn't noise at all. It had been sculpted. Like something, or someone, had intentionally encoded the sequence of the first 101 prime numbers into the deepest, most fundamental layers of cosmic light. The odds of this happening, naturally, vanishingly, incredibly small. Statistically, it's less likely than flipping a coin 1,000 times and landing heads every single time. It defies probability to an absurd degree. So, two possibilities rose from the data, both almost equally unthinkable, each demanding a fundamental shift in our perspective. First possibility: natural artifact. There might be some previously unknown, incredibly complex astrophysical mechanism. Perhaps a combination of extreme gravitational lensing interacting with quantum interference in a way we've never seen, never modeled, that somehow, under incredibly rare circumstances, mimics prime-based patterns in light's fluctuations. It would have to be a phenomenon completely outside our current understanding of physics, a long shot, a scientific Hail Mary. But science has been surprised before. Maybe the universe has a natural way of spitting out primes from chaos at its deepest level. Second possibility: intentional signal. This wasn't an accident. It wasn't a natural phenomenon. Instead, it may be a deliberate, mathematical signature encoded into the structure of the universe itself. If this is true, who sent it? An intelligent species? Perhaps not one like us, but one that exists in a parallel brain, managing to impress this pattern onto the light bleeding between realities? Or from something even older, something primordial, a cosmic intelligence, an architect of reality that predates stars, galaxies, and even time as we understand it? Because primes are universal. They don't depend on biology, chemistry, or even physics as we know it. They are baked into the fundamental structure of logic and mathematics itself. The sequence 2, 3, 5, 7, 11, 13. That sequence is true and fundamental in any universe for any intelligence capable of abstract thought. If any intelligence, anywhere, wanted to communicate across dimensions, across vast distances, across civilizations separated by eons or even realities, prime numbers would be the purest, most unambiguous medium possible. Just think about that for a moment. A message written in light, composed in the alphabet of mathematics, transmitted not through space as we understand it, but potentially through the very fabric of reality, the quantum foam that separates dimensions. Naturally, the team was intensely skeptical. They double-checked everything. Instrument calibration errors? Ruled out. Terrestrial interference from Earth-based sources? Cross-referenced and eliminated. Solar reflection anomalies? Accounted for. The pattern still held. Then they went one step further, a critical step to rule out their own instruments or methods being the source. They compared the James Webb quantum data with raw noise data from ESA's Euclid mission, which observes different sky regions using entirely different instruments from a different point in space, the L2 Lagrange point, but from a different orbit than JWST. Same pattern, same prime number sequence. No overlap in observation equipment, calibration, or local cosmic environment. The data couldn't be explained away as an artifact of Webb, or Google's processor, or their specific location in space. And at exactly 18 minutes and 30 seconds into the final review session that confirmed this, one of the lead investigators, a quantum information specialist not prone to poetic metaphors, leaned back in her chair, looked at the assembled team, and said softly, "This feels like a handshake. Not a signal in the traditional sense, not a message we can decode into words, but a handshake, a mutual recognition, a meeting point between our world and something else." a handshake across dimensions, encoded not in sound, not in symbols specific to a species, but in pure number theory, projected through the fabric of space-time itself. The implications, if this is real, if this prime pattern is truly intentional, are monumental. It would be the first mathematically structured non-human signal ever detected in the cosmos. And not from another planet, but from another reality entirely. A ripple in the quantum veil, a whisper through the gravitational mirror, a nod from something watching, something aware, maybe not life as we understand it, not biological beings like us, maybe not even consciousness in a way we'd recognize, but something capable of recognizing patterns, of understanding abstract mathematical concepts like prime numbers, and capable of embedding those concepts into the very structure of light that traverses reality. And what better way to say, "We see you, we are here," than with primes, the ancient, indivisible building blocks of all mathematics? If true, this would mark the real first contact event. Not with little green men landing on Earth, but with the fundamental architecture of the multiverse itself. It redefines what we mean by signal. It redefines what we mean by communication. And it suggests that maybe, just maybe, we are not the only ones doing the observing in this vast cosmic theater. Because for the first time, light itself may have answered back. What it means for reality. Let's zoom out, because what we've just uncovered, piecing together the anomalies from the quantum-processed JWST data, might be the beginning of an entirely new worldview. We started with raw, untouched data from the James Webb Space Telescope. Not the stunning processed images, but the fundamental photon information, the cosmic noise most systems simply discard. We fed that into a quantum processor capable of modeling entanglement across potentially billions of variables, a machine capable of acting as an unprecedented quantum observer. And what emerged wasn't chaos, it was structure. We found light distortions, arcs, and ripples bending in directions our classical physics couldn't explain. We saw non-local correlations between galaxies millions of light years apart, behaving as if a hidden variable, perhaps a parallel reality, was subtly shaping their positions and states. We discovered a gravitational mirror, a reflection of mass and gravitational influence from a place that, according to our standard models, shouldn't exist. A cosmic echo bouncing back from what might be a neighboring brain. But the weirdness didn't stop there. The quantum system picked up what looked like observer-linked phenomena, outcomes that seemed to shift or become more defined depending on how the quantum computer interacted with the raw data. A direct echo of John Wheeler's participatory universe idea. It was as if reality itself was participating in the computation, blurring the line between simulation and interaction. And then, the ultimate shocker. Something that stopped even the most hardened skeptics in their tracks. A prime number pattern embedded not in the signal, but in the noise of the cosmic light itself, across different sky regions, verified by independent data. Not a random fluke, not instrumentation error, but a structured mathematical sequence emerging from the deepest reaches of space. Let all of that truly sink in. It could all be an astonishing string of coincidences. That's the most conservative, scientifically cautious take. A handful of incredibly unlikely anomalies, perhaps misread or misinterpreted through the lens of brand new, bleeding-edge technology and humanity's innate desire to find meaning in the cosmos. It could be that. But maybe, just maybe, it's not coincidence at all. Maybe this is the first tangible, data-driven evidence that our universe is not alone. That what we call reality, our familiar four-dimensional spacetime, is only one layer in a vast, possibly infinite stack of universes, gently brushing against each other, interacting in subtle ways we're only now, with tools capable of perceiving reality at its quantum core, beginning to detect. A grand multiversal weave, stitched together by the fundamental threads of logic, probability, and quantum computation. Because if photons can tunnel across brains, if observation, especially by a quantum system, can shape the behavior of matter and light across potential dimensions, if numbers, the purest language we know, can pass between realities like messages in a bottle, then we're not just observing the universe anymore. we are communing with it. This isn't just science, it's something deeper. A confluence of astronomy reaching back to the dawn of time, quantum mechanics exploring the smallest scales of reality, information theory defining the nature of data, and metaphysics pondering the fundamental nature of existence. An inflection point where hard data begins to whisper the most profound philosophical truths. Maybe we haven't just built better instruments, telescopes capable of seeing further. Maybe we've cracked open a window into something vast, recursive, and alive with meaning. And now, standing at that threshold, one truth rises above the rest, clearer than the deepest web image. Our universe is not sealed. It leaks, it mirrors, it responds. And we, armed with quantum AI and a telescope gazing deeper than ever before, may have just heard the first reply, not in language we speak, not in sound waves traversing a vacuum, but in the only voice the cosmos has ever truly used, light. And light, it seems, is trying to tell us something incredible. We just have to keep listening and keep finding new ways to understand its message. This revelation, this potential glimpse of a larger reality, might feel overwhelming. It might challenge everything you thought you knew about your place in the cosmos. But consider this. If hidden patterns exist in the deep cosmic noise, waiting for the right tool to reveal them, what hidden patterns exist in the noise of your own life? What potential, what connections, what meaning are waiting to be discovered if you look with a new kind of awareness? If you use the right tools, whether that's curiosity, mindfulness, or a willingness to challenge your own assumptions? The lesson here isn't just about physics. It's about possibility. It's about understanding that reality, even on the grandest scale, might be far more complex, interconnected, and responsive than we ever imagined. It suggests that the universe isn't a cold, indifferent place, but potentially one filled with unseen layers, hidden interactions, and maybe, just maybe, even forms of consciousness or intelligence beyond our wildest dreams. So, my advice? Stay curious. Don't be afraid to question what seems like settled reality. Look for the patterns in the noise, both in the cosmos and in your own life. Embrace the weirdness. Because the universe, it seems, is stranger and more wonderful than we could have possibly conceived. And perhaps our role as observers, as questioners, as co-authors, is more significant than we ever dared to believe. What do you think these anomalies mean? Are we seeing ghost signals from reality's choices? Or something else entirely? Let me know your theories in the comments below. I read every single one. Thank you for joining us on this incredible journey through cosmic echoes and quantum whispers. Wishing you all health, curiosity, and clear skies. And if you want to stay at the absolute cutting edge of reality-bending science like this, make sure you hit that subscribe button and ring the notification bell. You absolutely will not want to miss what comes next.